So my name is Jacob Sisto. Today I'll be talking about soccer robots for everyone. If you would like to follow on with the slides, I have a TinyCC link there, tinycc/soccer robots. We're just going to talk about this project I've been working on for the past few months about soccer robots. So a little background on myself. I am a currently undergrad at UMass Amherst. I'm a senior in CICS informatics, so exciting senior semester at home. I enjoy working on a mix of projects that are kind of, is that possible? And then also have an educational aspect, either for myself or for other people. So I like building tools that teach people stuff, and I also like learning myself. So like some highlights of this is I've programmed an escape room at Puzzle Escape Games. I wrote one of the rooms so it is automized and kind of works like magic. And I wrote a Twitter client for the original Game Boy because I really like the Game Boy system. It's kind of interesting to me to see a platform that is so limited and what can you pull out of it. Like when writing this Twitter client, I had a piece of graph paper where I had a picture of the memory and I was checking whenever I used a memory address. So I remember, oh, I've already used this one. And then I got Minecraft running on an Apple Watch, just like fun little projects I like this. And I also like building bigger projects like the soccer robots one. And something I think the barrier for robotics and programming should be lower than what it currently is. Right now, I view that there's all these like things like, oh, you should come and do this program or go take this online class. And I think that it should just be integrated into everything. So you're always learning about robotics. You're always learning about programming because I think rapidly, as automation becomes bigger and bigger, this is a key concept that everyone should be learning. It's kind of background on me. I also work for Holyoke Codes, where we teach classes and camps and stuff, teaching robotics, programming, and other things. And then I have my own personal website, Orange the House, which is kind of like a blog that's kind of updated. I don't know. I updated it in batches because I've been migrating it over from an old version of it, but it gets updated. I occasionally lose the ability to click next. Okay. So kind of a background for the soccer robots themselves. In the summer of 2019, Holyoke Codes, we worked with the UMass soccer robots team, where they build these soccer robots to compete at national and world competitions to play soccer with robots autonomously. And we worked with them to build a program where the students programmed and kind of modified a little bit of the code for these robots, where they played a game of soccer, they played tag, and they played other things. And I thought this was really cool. It'd be like great if we could do this every week, right? But these robots are very expensive. I don't have an exact price tag, but to kind of consider in your head like how expensive these good robots could be, is that every part of them is custom machined, and the boards are custom built to connect everything. They require a special camera and computer to run and work with everything. So it's not something that you can easily just drag and drop. And then I talked to a grad student who works on it, and she walked me through kind of like the basic process of how to set them up and move them. And they take about half a day to a day of setup to get ready for moving and setting up and then resetting up somewhere else. And they have to be calibrated several times a day as lighting in the room changes or different events happen. And the field is very big, right? Like you can see here, it's taking up at least, I think it's like a 10-foot by 10-foot space of ground that not everyone has available. And these robots are also super picky. So they're machined with almost no tolerance. So the grates on the floor stop them from moving. So these are not very well adapted for a very expandable or movable situation. So I thought this would be a cool thing that if lots of people could get access to this. So why don't I work on something where everyone can use soccer robots? So when coming up with my own ideas for soccer robots, I kind of had three goals in the back of my mind while I was going. The first one being the robots themselves cannot be a barrier to entry. So the cost of the robots should be low. They should be reusable for other projects. And they should just be something that is easy to acquire, easy to get. Shouldn't be something that's like, oh, this is going to cost a whole lot of money. The second one is the programming must be accessible at every level. And what I mean by this is if you're just starting programming in elementary or middle school, you should be able to work with these robots. Or if you're in high school or college and you already have experience with programming, you should still get some kind of like enjoyment and be able to interact and learn from these robots. So kind of a wide range of programming levels. And then the robots should be able to work anywhere. And this is kind of like the main thing that I had when thinking about all this, because that was the biggest challenge with these ones, is they're super hard to move and set up again. And if you're going to schools, they could not have internet, they could not have any large table space, they could only have Chromebooks, right? So there's all these limitations that have to be considered. So we're gonna walk through each of these goals and how I believe I have solved them or how I plan to solve them in the future. So the first goal we'll talk about is the goal of the robots themselves. So the robots cannot be a barrier to entry. They must be small, cheap, easy to use, and just kind of work. So the first thing I needed was a processor to run the robots, because the robots themselves have to be really small. So like a microcontroller was the ideal thing. There's a microcontroller called an ESP32, which I really like. I have about 20 of them, and they are Bluetooth Low Energy and Wi-Fi capable. They're pretty small, like probably the size of 2.5 quarters. And they're pretty low power, so they're easy to use. But then as I was thinking more about it, they don't have this general reusability, because they're not programmed in a way that's easily expandable or compatible with a lot of things. Like they're like a traditional microcontroller, like an Arduino, or not a Raspberry Pi, but stuff like that, right? You have to program in C, or the Arduino software is compatible for them. And then they also have support through a thing called MongoOS for JavaScript programming. So then I started thinking about the BBC Microbit, which is a small, lightweight microcontroller that has Bluetooth and radio, as well as an accelerometer and gyroscope. It has a 5x5 LED array, and it supports GPIO pins, so the metal pins on the bottom. And it also allows for serial communication between devices. So this is a great platform. It's low cost. They cost about $15, but like a lot of these microcontrollers, you can't buy them by themselves easily. You have to buy these bundles. So I found they're like between $15 and $25 usually for one of them. Unless you can buy a bunch of them individually, which if you were doing a school project, you would do. And these microbits are not just, if a school bought these or a classroom bought these or whoever bought them, they wouldn't just be for this project. There's thousands of microbit projects that people can do. So they work very well in other things. So they're a good thing of like, oh, we can buy these for these projects, but then we can keep using them for this. And Microsoft MakeCode offers a block programming system for programming these microbits. So you don't have to know JavaScript or any of these other higher level languages. I programmed the microbits themselves for this project in a thing called MicroPython. And the idea behind using what I programmed is that the teachers or users will never actually interact with the software that runs on these microbits. They'll plug the microbit into their computer, select the like ID of the robot they want to use and hit flash, and it will just take care of it for them. What they will be programming is like on top of that, where they're communicating with the motors and the sensors and stuff on the field. They don't have to worry about the communication level stuff. Because the communication level stuff has quite a few interesting challenges, which we'll talk about right now. So communicating with a microbit, as I said, it's programmed on MicroPython. And microbits support BLE and radio. And I thought, well, BLE is the great choice, right? It's super easy to use. It's low energy. It kind of runs good. But the Bluetooth Low Energy library takes up a huge amount of space. So the reason I have a Game Boy on the screen here is that a microbit only has a tiny bit more memory than an original Game Boy does. And that's about 16 kilobytes of memory. The Bluetooth Low Energy library is 12 kilobytes. So if you're just using it for Bluetooth, you can use it. But if you want to do anything else, you can't use it because, at least for MicroPython, you have no space left over to actually execute the code you've written. So radio is way smaller. I don't know the exact number, but it's, I think, less than 2 or 3 kilobytes. So this is way more ideal for what I want to do. And then another problem is that now that we can't use Bluetooth, we have to use radio, is radio does not work with lots of messages. So in the system, I send about 100 messages a second, like telling all the motors what to do. It will, if you send messages that are longer than about 10 characters, it will start mixing the messages together. So you'll get like the first third of one message, the last third of another message, and then the middle of a third message in a random order. And it gets super confusing, or it just won't receive any messages at all, and they kind of just shut down. So I found 10 characters to be about the max for what it could handle continuously. And then 8 was kind of a safe thing under that. So I wrote this like little encoding of how you can communicate with the robots through the back-end communication. So the microbits on the robots are all listening for this sequence of characters being sent to them. So the first character they get is their ID. So they all internally have an ID. So if there's a message and the first digit contains their ID, then this message is for them. The second one is a color. So there's 10 colors they can choose from. This would be used for if you were doing like a tag game and you wanted to know who was it, or in a game of soccer, knowing who's on what team, you'd set the color, 10 colors, right? They're just basic like red, green, blue type colors. And then there's the actual driving. So the third digit is the direction. So this is either a 1 or a -1, indicating whether the motor should drive forward or backwards. And then the second, and then the 2 digits after that are how much power should be applied. So 0 is no power, and then 99 would be kind of as close as you can get to 100% power with the way it's set up. And then the same thing happens for the right motor. The kind of thing I want to optimize about this is that the motors on the robots, which I'll talk about next, only work at about 75% power. So if you're below 75% power, the motors don't turn on. So this could be freed up and written in a different way to kind of add the same level of speed control that I wanted, but kind of take advantage of the fact that like, oh, we don't have to worry about the first 75% of numbers because they won't actually make the motors move. And then all of these instructions come from a microbit that is plugged via USB into the computer the person's using. And they get their instructions from a Python app that sends the data to the microbit over serial. So it's kind of the basic communication of how the robots talk to each other. For the robotic platform itself, I'm going to use the DF Robot Micro McQueen, and I have quite a few of them. I learned about these at AppInventor Summit 2019 from a teacher or educator from a northern European country. I can't remember quite where. She let me borrow a microbit for a demo they were doing, and she had a box full of these robots, and I thought they were really cool. But these robots are super cheap, and they have tons of features built into them. So they're $25 for the base platform. Doesn't include the microbit. But they support up to 4 servos being attached to them. They have a built-in, like, are they on the ground sensor? They have a full ring of RGB LEDs around them. They have, like, I don't know, I would describe it as like an impact sensor. I don't know, they can kind of tell when they're being hit a little bit. And then they have a plug in the front where you can plug in an ultrasonic sensor into. So they have tons of expandability. They're only $25. And they're reusable for tons of stuff because they're running the microbit platform. So all those projects that you can use the normal microbit are super easy to use with this robot platform. And the people who make this robot have a library that you can easily install for the Microsoft MakeCode software, which lets you do microbit programming online. They have a library for that, so you just add that library and then you can access all the features of this robot. So this is a great little robotic platform. But kind of the limitations of this robotic platform and the limitations of the microbit is that it doesn't have enough power to do any computation itself. So it can't figure out where on the field it is, besides give some like basic information. Like if you have the ultrasonic sensor, it can tell you how far away something is, but it can't compute where it is. So we need a way to get the robot's location. So these robots are dumb and they only do as they're told. An external system will be needed to track their positions. it will also be needed to track the direction they're facing and then the ball they're trying to get or whatever the other objective is. This is very similar to the robotic platform, the original soccer robot platform that I saw that I'm basing kind of a lot of the stuff on. But I wanted it to be way more easy to set up where you could just plug in a webcam and it'd start working. So to do this, I found a library called ArUco, which is an open source QR code library that lets you do 3D tracking for robotics. Boston Dynamics uses it. You can see in this little GIF here of the ArUcos are what's on the boxes, and then you'll see in their other videos they're all over doors and other stuff.
And I thought I bought one new one recently, but I wasn't sure if that had already gotten eaten.
And the ArUcos are kind of, they have a unique ID to them assigned based on their resolution and their size. So their resolution is how many of these little pixels are on the screen. And then their size is the actual physical size. So in this video here, this is a resolution of 7 by 7. So there's 7 pixels per edge, and then it's 200 millimeters big. So that's kind of like the config you give to the library, and then it knows what it needs to track with from there. For this project, I'm using 100 millimeter markers with a resolution of 5 by 5, because I found if you go any lower, when you go far away from the camera, you start to lose your ability to track the robots. And if you go any higher resolution, then for cameras that have their own low resolution, the pixels start to blur together, and it can't track high resolution markers that easily, because they're like kind of indexed in a way, not like traditional image tracking. So the higher resolution is actually worse on lower resolution cameras. And then I chose the size of 100 millimeters because that's roughly the same size as this robotic platform. And ArUcos are pretty powerful. I would encourage you, if you're doing anything else 3D tracking wise, to look at them, because I'm using them for 2D tracking, but they work in full 3D space. And you can use them for like depth calibration on a camera, and you can do a lot of cool stuff with them. But I actually need to see the field and track some other stuff about the field. So for this, I'm using OpenCV, which is an open source computer vision library. And I'm using OpenCV combined with ArUco in 3 steps. So the first step is I apply a geometric image transformation to make the field appear as a rectangle, no matter what angle the camera's at. So this means the coordinates of the robot and balls are standardized and easy to track. So the best way you can visualize this is if you have a card and it's at a weird angle, and then you tilt the card so it's facing directly at you, or you could just take your hand and you're facing it directly at you. This is what the camera's doing with the computer vision and the processing, so that the field always appears as a flat rectangle on the screen. Essentially, as long as your camera is on the higher end looking down, the field will always appear flat, and the markers will always appear the right resolution, and it's much easier to track. And then when it's feeding that into the software, the coordinate system is the same no matter where you have it set up. Once I have this corrected image, I give it to the ArUco library, and it grabs all the markers, position, rotation, and the ID, and saves them into a temporary array. And then I do a color filter. So I filter the entire image looking for this color orange that this ball is here. And then I run a blob detection, which essentially finds the biggest clump of pixels. And that's most likely this orange ball, because not a lot of things are neon orange. And this lets me track the ball. You can see in this little video here, it's pretty fast and accurate, and you can kind of chuck the ball and it will still track it. And once it has all this information, it's packaged into a little JSON object and sent to a Node web server over a socket system that then shows on the coding interface a little virtual field where you can see the ball and robot positions, and it gives you feedback when you're programming. So that's kind of like this whole robot platform. So this kind of goal 1 accomplished, right? We have the robots that are simple, cheap. They don't require anything complex to get going. You just kind of plug the stuff into them, flash the software, and they're ready to go. And as a bonus, both the microcontroller, meaning the microbit, and the robotics platform, the Micro McQueen, are extremely flexible. And if you do the soccer robots and you decide, oh, maybe I want to do another project next, you can easily bring it all over. They have no, like, they're not rooted into this in any way at all. So the next challenge that I had to solve was programming the robots. So the robots need to be able to be programmed by students and users, and there needs to be engagement for every programming level. So if you're just getting started programming or you've been programming for a couple years, you need to be able to find something engaging and to do with these robots. So I kind of broke the programming into 3 levels of abstraction. So I'll talk about those, which starting with the like kind of most bare bones highest level, which is the JavaScript level. So this is the first level I will be kind of fully fleshing out, and this is what I will be using to program the other levels. So it's barely above the hardware level. It lets you do custom pathfinding. It's kind of exposing the I2C data ports, which is how the microbit talks to the rest of the robot, to the programmer, so that if you wanted to plug in 4 servos to these soccer robots, you could, whereas in the more higher level steps, you wouldn't be able to do this. And I kind of call it as like 0.5 steps above the communication library I'm writing, because it relies on the communication library to talk to the robots, but it's what I will be using to program the rest of the library. So it's kind of designed for more advanced users or classes looking to do something more advanced, like build their own pathfinding algorithms that you can't do with a simplified version or with the block-based programming. Well, I'm not going to limit you from doing it with the block-based programming, but I find that it's much easier to do complex things with actual code than to use the blocks. So kind of talking about the pathfinding for a second. The users will have 2 options. They can use a pre-built pathfinding algorithm that I've written, or they can make their own if that's something they want to do. Kind of a brief summary of the pre-built pathfinding algorithm I wrote is, I'm going to kind of visualize in these little pictures here. So you can imagine this red robot is trying to get to the ball. So it's going to draw a straight line from its position to the ball. And each robot has itself, which are the red and blue squares, and then it has this little bubble radius around it. And this is kind of like its personal space, right? If this line intersects with another robot's personal space, the line gets cut off at that point, and the robot will just pathfind to the edge of the other robot. So this pinkish light red one represents like step 1. So it was up in the top, it moved down till its personal space hits the blue robot's personal space. And now it's got this little separation here. And then it's gonna, the best way to describe it is roll along the other robot's personal space until this straight line to the orange ball is no longer intersecting any other robot's personal space. And this means that it's clear to go. This does mean that the personal spaces will overlap, but the robots themselves will avoid colliding with each other. What this thing can't do right now is it can't avoid walls, which is a key feature because these robots are kind of square-like. And right now, the algorithm that drives their automatic pathfinding doesn't know how to reverse, it just turns them in place. So if they go into any of the corners, they get stuck there because they can't turn in place without hitting either wall. So I need to teach it how to reverse and then how to pathfind out of that reverse. And this automatic pathfinding just looks for coordinates on the fields and navigates to the coordinates. So you can feed in the ball's position to navigate there, or you can feed in a random position on the field. You can feed in other robots' positions and build a game of tag where they're trying to get to each other. So you can do a lot of repurposing stuff with this. Kind of going back to the levels of JavaScript, we have level 2, which is what I call JavaScript, but with help. So in this, we have a block system where you can start programming the robot with blocks. Then we have a JavaScript side where you can convert the blocks into JavaScript and the JavaScript back into blocks and start seeing how these things interact. So the goal is this will be a middle step where students are moving away from just using blocks and are moving into the JavaScript library. But they can still, if they want to, go back to the blocks to see like, oh, I did this in the past. How does this look with JavaScript? This screenshot's here from Microsoft MakeCode, which allows you to dynamically switch back and forth between blocks and JavaScript. It's built on top of Blockly, which is a library Google made to program these block things, but then they also wrote it kind of in the reverse thing, where instead of going from blocks to code, you can also go from code to blocks. So I think that's really powerful. And then finally, the level 1 will be Scratch blocks. So this is kind of my first priority for the first interface and being able to use it, because I really like Scratch blocks. I think their colors are very positive, and it gives you like kind of motivation. It's like, oh, this is kind of fun to play with. The blocks offered in this level will have things like go to the ball or guard the goal, but I'm not going to limit users from using this environment to do the more complex programming stuff. So you can still access individual motor control. You can still tell a servo to turn on and off. You can still set the LEDs manually. I don't want this to be like kind of like a limitation. It's just a different way of looking at programming it. So it will have the simpler methods, but it will also have the more complex control that you can have with a normal, with like the traditional JavaScript library. It's just a different way of looking at it. So kind of building the Scratch interface is interesting because Scratch and Blockly, which Scratch is built on, are both completely open source for people to build their own platforms on. But Scratch has done something kind of interesting with their blocks, which is they have gotten rid of support for generators. So in Blockly, you have a definition and you have a generator, where in the definition, you design the shape of the block. So like the move 10 steps, this is where you design, like it will say move, it will have an input field, it will say steps, you can connect something in the top, you can connect something in the bottom. That's kind of what you do in your block definition. And then the generator says, when you hit generate code, if I see this block, what kind of code do I generate? So in this case, this is from a different program I wrote, where we have this fly forward. So when it sees the fly forward block, it's generating the code. It'll say, grab the distance from the block, put it into the string that says await drone.send, and calculate it that way. So this would be an example generator. But like I also mentioned, Scratch got rid of the support for generators. They opted instead to use this thing called the Scratch VM, which is a virtual environment that controls the Scratch interface. They want developers to move to this system, but it's designed for code that runs in the browser. And the code you write with the system does not actually execute in your browser. It's packaged and then sent to the server or the server, the like local server you're running in your computer, or the remote server. And that computes and then gives the robot instructions. So I need to be able to generate the code in the browser to send there. I can't run a Scratch VM. So I found a series of issues, like Git issues that were made from a while ago, where they removed this support, because I knew it's built on Blockly. It means they had to have had it at some point. And over the course of like 12 different issues and commits, they removed, added, and removed again support for this. And it's two people who are continually undoing each other's work, who are in favor or not in favor of allowing generators in Scratch. So as of right now, it's not in Scratch anymore. So I had to build a modified version of the Scratch open source code that has the newest version of the library, so I can use the new features and stuff like the undo, the kind of like nice looking way of the Scratch block. So it's not just Blockly. But I had to re-add everything they got rid of for the generators. But something they got rid of that's not in their code is they don't have any of the generators for the basic parts of JavaScript. So when you're putting a number in something, they have no definition for what a number is. They have no definition for what a Boolean is. They have no definition for what a string is. All of this is gone. So I had to go through and write essentially what is a number, what is a string, what is a Boolean when you're running this code. And then once I had all that, I could then start working on the new blocks with the new block generators. And a lot of the stuff with the blocks I've learned from previous projects where I've used Blockly. So kind of the two biggest previous things I've done with Blockly are Hermes and MinelyMod. So I'll talk about MinelyMod first, which is here on the right. So Minecraft in 2016, they added a feature for Bedrock Edition where you can write a mod using JSON, which is kind of a weird way to write a mod for a game. But you essentially put a bunch of tags in a JSON file, you package it up, you drop it in your game folder, and it will modify the game to be whatever tags you put in there. This requires you knowing the structure of JSON. Each of these tags are like 30 lines of JSON, so they're not easy for people to get used to. So I thought, what if we build a programming environment where you just, each tag is a block, you drag out under the mob you want to change, hit save, it saves it to your game. So that's what I built for there. Unfortunately, MinelyMod is not still running because they update the game almost every week, and it's very hard to keep up with, and I haven't had time to keep up with all the changes they do every single week. So right now it's not active, but in the future I would like to reactivate it again. And then right now I've been working on Hermes, which is a software that allows you to program the DJI Tele drones with Scratch blocks. And this is kind of where I did a lot of the development on getting Scratch from its Scratch VM back to being able to generate code like Blockly. So Hermes lets you build the block code, and then it generates the JavaScript, as you can see here. So the async function, green flag, sending the code. And then this is actually a kind of like basis for how the soccer robots work, where this code is not run in your browser. It's captured, sent back to the local server, which in this case is just an Electron app, which is executed and sends the drone commands. So this same system will be used, but instead of sending it to an Electron app, we'll be sending it off to the server to do the calculations for what the robot should do. And this is where I did a lot of the heavy work on getting Scratch blocks usable for projects that are generating normal code. Hermes can also remote control the robot and view live view video. I will be hopefully releasing some kind of version of it in the near future for a lot of other people to use. But moving on to kind of finishing up the coding stuff, we've kind of accomplished the code goal. So the robots can be programmed, and we have support for people who want to do the heavy JavaScript side, for people who want to use Scratch, kind of this huge range between. And now we have the biggest and most complex goal of it all, which is the robot should work anywhere. And this is something that was kind of the first issue I thought of. But I'm calling it goal 3 because it's kind of the most futuristic goal, because everything else has to be built before this goal can be approached. But there are a lot of important questions when building something to work in classrooms, because classrooms are very different environments than something that someone with a computer would normally have access to. So kind of like the big questions I thought of is, what if the school only has Chromebooks? What if the school has no computers that can run Python or aren't powerful enough to run OpenCV? And then kind of like the biggest major one is, what if the school has no internet and they need something that can run locally? So these are all things I have thought of and designed out a plan for. Some of them I've built like prototype versions of it. Some of them I've actually developed, but we'll just talk about each of these problems as we go. So the first problem, and I think the most likely problem that schools will run into, is that they won't have computers that can run the software, either because they're not powerful enough, or that software can't be installed on them, or they're Chromebooks or something like that. So in this case, I have 2 solutions, one being the future solution that I plan to use for the future, and one being my current demo and testing version. So for the long run, I want to use AWS with a P2 instance. So AWS P2 instances give you a dedicated GPU that is powerful enough to run about 12 or 15 of these soccer fields at one time. Combining that with WebRTC, the latency in the video will be almost 0. And the video itself doesn't have to be then sent back to the user. Just the instructions for the robots has to be sent back. So the user can just log into the website, say, I would like to use a virtual GPU. They set that up, they plug in their devices, download some kind of plugin to connect to it, and then all of the computation and thinking is being run remotely, and all they have to have is the robots themselves. This would come as a cost because AWS P2 instances cost about $1 an hour. But I don't want to charge any more than kind of a little bit over what it would need to run. And the way it'd work is, say you needed to use it for like 1:30 to 3:30, you'd log into your portal, say, this is when I'm using it, hit launch. After like, when there's 15 minutes remaining, it's sending you a reminder saying, hey, you're about to run out of time, would you like to renew this? And they just prepay for the time they're going to use on it. The second temporary solution is using my own personal server. I have a server I use for training machine learning models, and I run a bunch of bots on it for various chat clients and stuff. And this server, unlike a lot of other home servers, has a pretty decent GPU because I use TensorFlow a lot, and GPU training TensorFlow is really good. So I put a pretty powerful GPU in my server, and this server could run 4 to 5 of these fields, and probably even more depending on how many robots are being calculated by itself. And I have a fairly decent home network connection, so for initial like 2 or 3 people testing this out in the field, this could run most of the plans. And it'd be easier to build up the software on this local system with Docker containers that I could then just port straight into the AWS thing when it's ready to launch. So if all the stuff is running in the cloud, the kind of thing becomes, well, then how do they talk to the robots locally? Because if you remember before, I mentioned that there's a microbit plugged into their laptops that allows communication with the microbits in the robots out in the world. So in order to connect to that, I'm going to use Chrome hardware interfacing. So this works on Chromebooks, it works on Windows computers, it works on Macs. And I don't know how many people know about this feature, but Chrome offers hardware level access to applications running in the Chrome browser. So on your website or in a Chrome extension or a Chrome app, you can access the hardware devices of the computer you're using. And through this, I can kind of get rid of the Python app that currently handles communication with the microbit, build a Chrome extension that takes the data from the remote GPU server, builds the serial package, and then using Chrome, send the data over serial. And this is pretty powerful, what Chrome can do with this, because nothing has to be on their computer at all. It can all be remote. All they have to do is plug in their USB device, plug in their USB microbit, plug in their webcam, and that's all they need, like physically ready to go. They can have they could have the most basic Chromebook and be able to run this. And Chrome hardware interfacing can do a lot of stuff. It can do serial, but it can also do a bunch of other USB stuff. For instance, the Nintendo Switch, you can homebrew it, which allows you to install custom software on it. Someone wrote a tool that can homebrew your Switch by plugging it into a Chrome app. So you don't need to do anything great, like you just plug it in and it does it. So Chrome hardware interfacing is pretty powerful. It will be kind of like the link so that all of this can run on a Chromebook. But then there's kind of like the biggest and last challenge, which is what if there's no internet at the location? So for this, I'm borrowing an idea from MIT AppInventor. So AppInventor makes a website where you can build iOS and Android apps natively in your browser, and it will compile them and give you the APK to install on your phones. And this requires this full web stack to build the files and generate everything. But they built a version of their entire web stack that runs on a Raspberry Pi, which is a small computer. It's like $35 to $50 now. And this is something I want to be able to do. The problem is most Raspberry Pis can't actually run OpenCV at any real frame rate. The Raspberry Pi version 3 can run at about 12 frames a second, which would be fine if you had one robot on the field, but if you have a bunch, you're trying to avoid them hitting each other, it's just not fast enough. But the new Pi 4 has its own dedicated GPU chip, and this could mean, I don't have one yet, this could mean it could support like 2 or 4 robots on the field at any one time, and it could do all the calculations. And then AppInventor's version also sets up the Raspberry Pi to run as a network access point, so you don't even need like a local internet connection with a router. You can just plug in the Pi into the wall. If you have a Chromebook, connect to that, and you'll have connection to the soccer robots. So it's kind of like the last thing I want to do, because this will require everything else to be built out and optimized before I can start working on the Pi conversion. But this will be kind of like the ultimate goal of portability and working everywhere is, could I put it on a Raspberry Pi that someone could, that I could lend to someone, or they could just buy some flash their own image and set it up themselves, and it'll all just be on there and work.
Hey, Jacob,
kind of the future for this project.
Just flagging that we have about 5 more minutes here.
Yep. So kind of the future of this project is, right now I only have a basic JavaScript library that can do basic tracking of the robots and send basic commands to them. So before I do any real testing with students, I need to build this out to at least have the full Scratch interface that we talked about. I also want to prioritize the virtual and remote GPU system, as I think this will be a key feature for getting schools on board. If we can say, you don't have to have anything crazy to run this, you can just log into this website and it will work. And then kind of now that we're all at home, I want to build a system where people can, through an interactive live stream, program and drive the robots on a Twitch stream, where anyone can just log into Twitch stream and say, I want to control robot number 3. They get a panel if it's open, and they can start programming it and watch the robot do stuff on the stream. So these are kind of like my main next goals for this. So kind of, this is kind of the end of my soccer robot talk. So kind of my information. So my GitHub link is there. Most of my stuff is on there. My website, like I said, has kind of like blog post style things, but they're updated randomly in weird batches at different times. My Twitter, I post updates about stuff I'm working on there. If you have any questions, you can email me at jacob@orange.house. And then I build custom software solutions to unique problems. So if you have anything that needs solving, let me know. I've programmed escape rooms, how-to balloons, done plenty of block-based programming environments, and I've done some more niche stuff like the Minecraft on the Apple Watch or Twitter for the Game Boy. And again, if you want to have the copy of the presentation slides, they're here. If you have any additional questions, I will be using the remaining 5 minutes for that. So, I see chat now. So someone asked, what GPU do I have? So in the server GPU, there's a 2070 Super RTX for that GPU. It's plenty fine for stuff. Are there any other questions people have? Yes, thank you for listening, and I hope you continue learning about the soccer robots. I hope by the end of 2020, something should be there that people can use.